All right, so first, let me remind you quickly what we have seen last week. I firstly introduced or mentioned what is the information model. It's made of 3 components. I will not come back on it, but there were 2 interesting things based on this. What is the common knowledge? And I emphasized last week, common knowledge is not only something that everybody knows, but it's also something that everybody knows that they know it and so on. So you need to think a second about this. And this updated belief, it plays a role, and I will come back to it, but it means if you have even if what happens or the state of the world is unique, depending on a kind of partition of all state of the world, your understanding can be different for each player, even if it's the same state of the world. Then I introduced these strategic games with incomplete information. And in fact, we dealt with them last week, and we are going to continue today. So they are called, I emphasize finite, because today I will cheat a little bit. So I gave the definition for finite Bayesian game. It's made of 5 things, and I recall them here. So the first one is a set of states of the world. This is what nature gives you, so it's based on some randomness. Nature decides something, and it takes one element in this set, but a priori you don't know which one. Then you have the type. The type is precisely an information that each player has. The player knows his own type, but not the type of the other one. So this is a private information. Your theta I, let's say I'm player I, I'm the only one who knows the value of theta I, and you know the value of a different theta if you're a player. Okay, so this is something new compared to what we have done so far. You have an information that nobody else has. So this vector, we have n players, theta 1 up to theta n is called a type profile. Then we have a probability function rho on the set of all types profile and the state of the world, all state of the world. It means at the beginning, everybody knows what is the probability to have each type, what is the probability to have any state of the world. This is a common knowledge. But then you are going to get your own type. Now, the set of actions, so A is a set of what players can do. So player I can do different things, and all these things are encoded in the set AI. And the payoff. Now the payoff is a bit more complicated because it depends on the state of the world, some randomness. It depends on the payoff for player 1, it depends on your type, but you know it. And it depends on the action of all players. So we will see, in fact, most of this lecture today is based on an example in the second part. So Bayes' game is these 5 objects. And as I emphasized, once a player I knows his type, he's going to update his belief because all players had a common belief, which was this. But once you have an information, you can update this. And I gave a formula for, so this new or updated belief is a probability function, no more on this entire set because you have one information. So you only have theta 1 up to theta I minus 1 and I plus 1 because you know precisely the value theta I. And it also depends on the state of the world. So it's a probability function on a slightly smaller set compared to this. And I gave a formula. It's based on Bayes' formula. That's why it's called Bayes' games. And again, this is an updated belief based on your knowledge of your profile. So it's an information that you are the only one to have. The updated belief is something private. Now, we have seen at the end of the lecture, I gave an example. It's difficult to write a complete recipe, but it's easy to guess on examples that any finite Bayesian game can be represented with a tree, and more precisely with this extensive form game, which is what we did in the previous chapter. So you can construct a tree. This tree or this extensive for game has imperfect information because of this. You don't know the type of the other players, but it has perfect recall. And this perfect recall is an important result, or it's an important property we have seen. So I gave you an example last week, and there is another example in the notes. If you have any question, you can ask me. The same for those online. If you have any question, you can always interrupt me. So today we continue, and as I said, we will play a long time with one example. Okay, so far I just described the framework, but I did not say what is a strategy. So what is a pure strategy? Pure strategy for this game. It's a bit more complicated. Pure strategy for player I is a function. You will see why it's slightly different. It's a function AI, but I put a hat from this set theta I to AI. Why? Because at the beginning, you don't know your own type at the very beginning. So you are going to act, you have different possibility to act depending on all the types you can take. So it's a function of all possible types that you can have to the set of pure action. So this is what you do. But this action you do depends on your type. That's why what is called a pure action is a function from depending on your type. Then you are going to fix it in the set of all actions. And the set of pure strategies. So this is a strategy for player I. So the set of pure strategies for player I is denoted by player I is hat. So A hat. So this was the action. Now this is the set of function from your profile to the actions, and all these functions are denoted by A hat I. And what is capital A hat? You can expect it's a product for all players. This is the set of pure strategy profile, pure strategy profile. So the only difference before a strategy was the choice of an action. But now this action depends on your profile. So it's a function on this set. And for, if the other players want to know what is going to be your action, since they don't know your profile, since they don't know your type, they have to consider all possibilities. So for them, it's really a function from all possible types for you to the set of all possible actions you can have. And we write, this is just a notation. So if I take an element which is A1 hat to AN hat. So this is an element of this type. And I'm going to write A hat of theta, which is A1 of theta 1, A hat 2 of theta 2, or to A hat n of theta n. So just check that it's meaningful. So a pure strategy profile is a collection of pure strategy for each player. So it's this collection. And when you fix this theta is a type profile, so it's a theta 1 up to theta n. Then when you associate or when you apply this to a theta, it's the first pure or the pure strategy of the first player, which depend on the theta 1, the pure strategy of the second player, which depend on theta 2, and so on. So it's meaningful. So it's a notation. Okay. But please keep in what is really important in this topic is that player I know only theta I and not the other one. This is important. So we know what is a pure strategy. And you know, this we are dealing with a game where we have only each player is playing only once. We could iterate this, but so this is why this action contains only one action. This pure action is only once. Okay, now we can just go to the next step. So once you know, okay, let me call it. We have already done it. Once we know, or once each player knows his type, we have already updated the beliefs. We have the updated beliefs. And we can also update the payoff, because the payoff was a function depending on all possible type. So now if each player knows his type, we also have to compute exactly these updated payoff.
State of the world.
Yeah, the state, yeah, it will depend. The payoff will depend on the state of the world. So now we compute these are the new payoff or the updated payoff, because we have one information. So let's check what they are. The payoff for player A, for player I. Always use the payoff for player I put a hat because it's going to be the updated one once we have the information of the type. I'm going to write a formula and you will see that it's the only one we can have. So for player I, he doesn't know the type of the other one. So he will have to take all possible type for the other player. That's why he's going to sum over all types for the other players, not himself. Lambda, he doesn't know the state of the world. So he's going to add all possible state of the world. And what is the expression? So it's a big sum of the updated belief, which depend on theta 1 up to theta I minus 1, theta I plus 1 up to theta n, and lambda. This is the updated belief. We have seen that it depends on all variables except the theta 1, the theta I, and then the payoff of lambda theta I and A hat theta. So let's check that it's meaningful, and there is an I. The payoff was depending on the state of the world. the profile of the player I and the actions of the other players. So it was a function of these three things, and what the player I can expect is this sum over all updated probabilities of this payoff. And be careful, there is one thing which is sometimes a bit disturbing. If you compute this on a concrete example, I'm saying that it doesn't depend on theta I in this formula, but if you do it concretely, it will depend on theta I, because this guy, I gave a formula, this guy is computed with the information of the type I. So if you write this explicitly, it's possible that in this you would have exactly the type theta I which will appear because it's encoded. But this information is used. You don't do a sum over theta I because this is what you know. You have a question?
Yeah, the state of the world in the row I is different from the state of the world in UI, right?
No.
Because
no.
the world change.
No. There is only one state of the world. But you don't know it, but there is only one. So it's in your updated probability, and it is also in the initial payoff. So this is an updated payoff because you have an information. Keep it in mind. So again, this is a private information, so let me emphasize it. This information is private because it uses the information theta I, and you're the only one to have this information. So the other one do not, that's the difference between what we have done up to now and what we do now. Before, everything was visible for all players, except your action. But now, they don't know how you're going to compute your payoff. They don't know the payoff that you are going to compute because they don't know your type. They know they have the information for themselves, but not for you. Okay. So this is pure strategies. And let me just say orally, it's written in the notes, but we can also define behavior strategies, which are probabilities on the different possible actions. You can define mixed strategies, but for our purpose now, it's enough. But what we have done before can be applied to this, so behavior strategies and mixed strategies. And the mixed strategies and behavior strategies are not very different because of a theorem which I mentioned, which is called Kuhn's theorem. We have seen that when we have perfect recall and we have this situation, we are in this framework, mixed strategies and behavior strategies are the same. Okay, so I don't want to spend time on this, but I've wrote one paragraph in the notes. Okay, so now we have all the ingredients. We started with this common knowledge, then each person knows, or each player gets information about his type. The player updates his belief, and he can update the payoff. So we can now discuss what is Nash equilibrium, and it's not different than what we had before. So for Bayesian Nash equilibrium, so you can expect exactly what it is. I call it B star in the set of A star. We can define it also for behavior strategy, but I define it for pure strategies. So is a Bayesian Nash equilibrium if the payoff at B star is given by, or is included in argmax. I will explain again on I hat of oh, I should use A. Sorry, I changed. It's not the letter A instead of B because I define A. So A star. A star 1 up to A star I minus 1 dot A star I plus 1 A N star. So and I can put a hat everywhere in order to be consistent. So this is the usual definition. We are for player I, you don't know the strategies of the other one, but you are, for any possible strategies, you choose the one which gives you the maximum payoff. So it has always been like this. We look for A star so that when it's for player I, it gives you the maximum payoff among all possible pure actions. So if you compare, it's the same as before. And the expression for UI, did I put a hat? Yes. UI hat of A is written here. So there is no difference. And again, we will have very soon a concrete example. Unfortunately, there is a theorem which says that for every Bayesian game has at least one Bayesian-Nash equilibrium. So for all games I have introduced so far, we had always such a statement exists at least one, which satisfy our requirement. By the way, argmax, I encourage you to check what it is. I already mentioned it 2 times. It's an important notion. You look for the variable where this function takes its maximum value. And it's an inclusion, it's not, it belongs to. You may have more than one point, so it's not an equality. Okay. So let's be more concrete. In the notes, I mentioned that there is one famous example on, I encourage you to also look at this, which is called the chain store paradox. One student has already started working on this, but we can improve and you can also work on it. And I'm now giving you a second example. Yes.
Every time game has at least one Bayesian-Nash equilibrium in behavior strategy.
It's also true for this one. Yes. Yes, that's why I simplify. I don't want to mention here again behavior because in application, we look for pure strategy. We don't look for probabilities. Yeah. But yeah, I cheated a little bit compared to the notes. I agree. So let's look, as I said, as a concrete example. This is the next section, which is auctions. I already mentioned first price auctions, first price on second price auction a long time ago. So it was in chapter 2. First price auction, second price dimension. In chapter 2. And in fact, I cheated at that time and nobody observed it except one person. Why? Because it's an auction, so it means everybody we want to sell something. Everybody has a price in mind, but at that time, there was no private information. And it means I already used the letter probably VI, and I said, oh, this is a price that player I has in mind for this object. But if you look carefully, it was an information that everybody would know that you give this price to this object. Because at that time, there was nothing private. Everything was known by everybody. So it was not very realistic because the price you have for this object would be known for everybody. Now we have the notion of private information, so we do it correctly in the sense that if you think that this object has a certain value, you can keep this information just for yourself. So there was a mistake. It's not a mistake, to be honest. I even wrote to the author of the book saying, oh, please, you are cheating in this part. And he said, yes, but look on chapter which correspond to this one where we do things correctly. And indeed, this is now we can do it correctly. But at that time, we had no private information. I will recall what it is. But now we can do it better. And a remark, and I feel a bit embarrassed with this. You observe that I introduced finite Bayesian games. And I told you what it is. I will now drop this finite without giving you the precise theory. Why? Because if you try to write the general, it will be clear in the application. But if you try to write this from the beginning without this finite, you end up with the notion of conditional probability. And conditional expectation. And for those who have taken the course on stochastic calculus, you may remember that these notions are not simple. So I didn't want to introduce this notion in the continuous case. So that's why I introduced finite Bayesian games. And now we will use them for continuous, but you will see there is not so many differences. But the general theory would be a bit more involved. So I didn't introduce it. So I prefer to introduce it on an example and not in the general framework, because conditional probability and conditional expectation in the general case are a bit complicated. But you will see, it's not so difficult. In this example. But usually I try not to change the formalism. Okay, so what is the framework? We still have n players. We have one object. My favorite object. And there is a value. We need an upper bound. So I will call it nu or v bar bigger than 0. The maximum value or the maximal value for the object. We will see why. We just need. So nobody would say that this is worth more than 1 million yen. So you can fix 1 million as an upper limit. That's it. I don't want to go to infinity. This is the maximum value for this object. So it means the value for the object will be in the interval 0 and this maximum value. We cannot expect it to be bigger. Now we do an assumption. We assume, so everybody is going to have in mind a price for this. You are all the players. You have in mind a price for this. And I'm going to assume that it's called a valuation. So assume all valuation. So the price you think for this object, all valuation are independent because you are independent person. So that's quite natural. They are independent and identically distributed. What do I mean by this? So okay, this is the price you have in mind for this object. Probably you are all going to say, oh, it's not 0. Maybe I'm going to give a price like this, and it's again 0. So you are going to choose a price between 0 and this maximal one, and probably it will follow a certain distribution. And we assume that for all players, they are going to have the same distribution for the possible values. Okay, so this is a distribution and this distribution is called, I call it red row. We will see that there will be a red and a black one. So they are all independent and identically distributed following the distribution row. So this is the assumption. Okay. Now just a technical assumption, but it's not important. I will assume this function to be differentiable. But we assume that this row is differentiable. And of course, if I have this upper price has support on 0, it means away from this interval, you are not going to put a negative price, but you are also not going to give a price which is higher than this one. So it has the support of this distribution is in this interval. So I emphasize once again, all players know, all players know this function rho, but each of them choose a specific theta I according to this distribution, according to rho. So it means in this room, probably one student will choose this one. This is the first one. Another one will choose this one. Heavy do will choose this one. This is heavy do. But there is still a chance that somebody choose this one, but most students would probably choose something here because it has the biggest value for this distribution. So all of you have in mind a certain price for this, according to this distribution. No, heavy do.
No, I want three. I want zero.
No, you're not allowed. I will keep it. Sorry. And again, this distribution is known by everybody. So now I gave you the framework. I want to put this in a Bayesian game. So I need to remember a Bayesian game has 5 objects. So I need to tell you who are the 5 objects for this game. And then we are going to play. So this information, this is a private information. This is private. You are the only one who knows the price you have for this object. So I'm going to say that it's a game with incomplete information. So let's check what are the different objects. First, lambda, there is nothing random. So I already mentioned when there is nothing random, it's just 1 point. There is nothing to decide. Okay, so I already mentioned this. Now, the different type. So what is capital theta I? This is the different values that you may give for this object. So it is this interval. And this is where, if you check compared to the general definition, I cheated because I said it's a finite set. Now I take it a continuum set, but we can survive. So it means this one is n copies of this, because we have 1 copy for each player. And inside this set, theta is simply a theta 1 up to theta n. We have n players. So each player has a type or a price for this object. Here, the type is a price for this object. What is rho? Remember, we have a rho, which was a probability on what it was called this times capital theta. You can forget the first set because it is just a point here, so it doesn't play any role. But it's a probability on this set. Can you guess what it is? Each of you has the same rho in mind. So in fact, it's what we call a product probability. So I just write it, but this rho is in fact rho times rho times rho, because each player has the same distribution in mind. So the common knowledge, this is a common knowledge, is just made, oh, the first player has this in mind, the second player has this in mind, the nth player has this in mind for the price of this object. Yes, that's why I put a red on the white. The red is for each person. It's the same for each individual. They could be different. I could do something different, but I do the simplest case, and this is a common one. Yes?
One. But red does not have any normalizability.
Yeah. It's a probability distribution.
Oh, it's
okay. No. Okay, be careful. This integral is 1. The integral is 1, which means this is a probability distribution, because all probability distributions sum up or integrals is 1. Yeah. Okay, I should have maybe mentioned the probability. Okay, the probability distribution rho. And now we need an object on this, which is n copies, because we have n players. It's just a product. And in order to be perfect, you should put a circle here, because this is a correct notation. But keep in mind, for each player, we have one probability distribution. And you can check the integral. It's like an integral of n variable for a function which is a product. You end up with 1. So it's again a probability distribution. Let me keep this for a second. So I already gave you 3 of the 5 objects. Then we have AI. This is number 4. AI is a price that you are going to say. So you have in mind a price, but when we play, you may say something different. So this is your action. So on A is 0 infinity. And this is an action of player. So for here, action of player I, in fact, it's a bid, or what you are going to say for this object, the price you are going to say for this object. Okay, maybe you are going to say a bigger price.
But you said big one.
At least here I can do it. There are some technicalities. And okay, so this is the action for player I, or the bid, and the payoff U, which is going to depend on which auction we are playing. So I will give you 2 examples later, but now we have to know that this depends on the times AI is valuing half. This was like this. Payoff depends on your type or on what you have in mind for the price and on the action. Wait, I think there is no I. UI. Oh no, UI. Just need to be sure. Does it depend on? The UI, no, it's a function of A, not AI. And I will be more concrete when I give you an example in a second. So now we have seen that with this game, we are exactly in this framework, and I gave you all the objects. So this depends on the type of auction, And we will see 2 different ones in a second. And I need to add one thing that I mentioned already in chapter 2. In case of a tie, which means 2 or more players propose the same price, we need to decide what we do. And in this case, we are going to put the same probability for each player. To get, but also to pay for the object, to get the object. So it means if 2 persons propose the same price, then we have 50-50 chance that one will get or the other one, and of course the one who gets it is going to pay. Now, as we did in chapter 2, there we present two types of auctions. There is a first price auction and the second price auction. And the only difference is in this UI. So what is the first type auction? First price. It's not first price. The type is something else. First price auction. So we denote by U. I put a capital I or 1 because it's the first type. It depends on theta I and on A, as it has to. And I give you a formula. So this payoff is, for player I, is theta I minus AI. We will understand. If AI, I need more. The first case is the player I is the winner. If AI is bigger than the maximum on J different from I of AJ. Remember, AJ or AI is a price that you propose for the object. It's not the one you have in mind, it's the one you propose. So if AI proposes something bigger, he's going to win, but he has to pay, or his payoff is the difference between the value he's seeing for the object and what he's proposing. We have already seen this. Now, if there is a tie, so it's theta I minus AI divided by the number of J, so that AJ. It looks complicated because it's precise, but you divide by the number of players who propose a maximal price. The set of the number of players which propose a maximal price. So the payoff is the same, but divided by this quantity because you divide by the number of players, the probability that you get the object. So this is if AI is equal to max J different from I of AJ. Look, the meaning is there are at least two players which propose the same price. And if you propose something lower than somebody else, you get 0. So if AI is strictly smaller than the maximum on J different from I of AJ. So the first case is when you win. The second case is when you are among those who propose the biggest price. And the third one is when you propose something which is lower than the maximum. This is the first price auction. And I recall with A is the action of the different players. So it's A1 up to AN, the action. And in this case, it's again the bid of all players. Okay. Yes.
Be theta I minus AJ, where the payoff is the value you would have saved by the amount if the other bidder has bid more than the value that you have.
You mean for this case?
Yeah.
No, because you don't get anything. I mean, you propose a price, you don't get the object. What is your?
But the other.
No, but you have in mind a certain price. You think then somebody else is going to buy it. You don't win. You don't lose anything. So no, that's natural that it is 0. If you are not the one who win, you don't lose anything. It's just an experiment, you thought about one price, that's it. No, that's fair. Otherwise, you would play all the time and expect to lose because each time you will win something. No, that's not correct. Okay, this was first price auction. For the second price auction, I need to introduce an object which I haven't seen in the literature, but I introduce it. So what is the second max? We know what is the max of a set. But what is the second max? Of course, you have an idea in mind. If you take a set of numbers, you eliminate the first one, then the second biggest one is the second max. Oh, yeah. But how you define it? I mean, this is, you cannot write this. So how you define it? You define it as a max of the set A1 up to AN minus the maximum. And it's meaningful. Look, you take this set of n numbers, this means you remove the maximum, and maybe you remove several terms which are the same. So no problem. If 2 are the maximum, you remove these 2. And then once you have done this operation, you take the maximum. And this is the second max. If all are the same, yes, you remove everything, but this is quite rare. So now we have a definition of the second max. And we can define a second price. This is a second price auction. So I'm going to call it with a 2 here. And I need to change this formula. So the difference is you don't pay the price you propose, you pay the second price. This is I already mentioned this in chapter 2. So in the second price auction, you are the winner, but you don't pay the price you propose, you pay the price that the second one proposed, which is also a good idea. So you propose, if you're the winner, your payoff is theta I minus the second max of A1 up to A. Oh, no. Yeah, it's the second max of A1 up to AN. But what is the condition? If AI is the same as before, is bigger than the max J different from I of AJ. So if you propose something bigger than all the other one, your payoff is what you expect minus the second price. If we have equalities for different players, minus second max of A1 up to AN, and it's again divided by the number of person who play the maximum, AJ equal to max AK. So I'm just dividing by the number of players who offer the same maximal price. If AI is equal to the maximum J different from I of AJ, the same condition as before, and we do it again 0 if AI is strictly smaller than the maximum J of AJ. So the only difference is you don't pay the maximum price, you pay the second max. And it makes a difference. So let me emphasize one more. Remember, theta I is known only by player I. The other one do not know it. It means this computation is not known by the other player. It's known by you, but not by the other one. Okay, so be careful about this. So once we have this, the next step was to compute the updated belief. Remember, rho I of theta 1, theta I minus 1, theta I plus 1, theta n. I did the computation in the notes. Either you do the computation and you follow, or you can guess the result. Because remember, this row is made of a product. Because all the distribution for theta, for the price you think about the object, is the same for all players. So it follows from this independence that you're going to, you can do the computation, but you can also guess that this is going to be rho of theta 1, rho of theta 2 up to rho of theta I minus 1, rho of theta I plus 1, up to rho of theta n. Again, either you do the computation, or if you think about it, because of the independence, you have to get something like this. It's not a surprise, but it follows from the definition on a small computation. So we have computed the updated belief. And in this case, you observe that it doesn't depend on your theta I, which it could in general. Then I recall a pure strategy. I just recall what it is. Pure strategy for player I is AI hat from this set to AI. And I remind you, this set is 0 new to 0 infinity. So this is just recall what it is. And the last object I can compute is, we have here the payoff, the general formula. We have the updated belief. So we can compute the updated payoff, because you know the value you are going to give to this object. So this is the general formula, but it doesn't take everything into account. So let's just put a formula for the updated payoff. So the updated payoff now. Updated payoff is, so it's valid for both game I or the same formula, because it's just a general formula. Why I want to write? Because before I wrote it with a sum, we were in the discrete case. Now we are in the continuous case, so I have to replace this sum by integrals. That's why I want to write. And probably I haven't written any integral so far. So if you haven't seen me writing any integral, you may be surprised. I put, an integral is just a notation. So I usually put this which for some people would be put at the end. I put it close to the sign integral. It's just a notation. So be careful. It's a notation. It's convenient when you have multiple integrals. So if you don't like it, you can put these there, or this at the end of the line, but I prefer like this. So what was n sums, or n minus 1 sum, is now n minus 1 integral. And what we need to integrate, we integrate the updated function which I have written here, times, so it's times u either 1 or 2, depending if we play the first auction or the first price or the second price auction, I of theta I a hat. There is nothing here. I just replace some sums by integrals. Okay, so what we can do with this? I need now to give you some results. Because if you want to play this game, you need to know what to do. What is the best strategy? Or the Bayesian-Nash equilibrium? And in fact, here I put 1 or 2, but depending if we play the first price auction or the second price auction, the results are not the same, quite surprisingly. And the second one is easier. So I will start with the second one. There is a proposition which, if somebody hasn't done any report yet, this is a possible one. It's not so difficult. So for second price auction, and for any I, for any player, for any I, the best, oh no, let me write it first, sorry. It's not the best. I. Okay, of course, I'm using something I introduced already a few weeks ago. So what does it mean? You have in mind the price theta I. The one possible action is to say, oh, I propose the price I have in mind theta I, and it turns out that it's a weakly dominating strategy. It means it's better than any other strategy locally. So you can look at the meaning, but we have seen this. So it means for second price auction, proposing the price you have in mind is a good idea. And surprisingly, it's not the case for the first one. We will see. So this is rather natural. You are going to propose the price you have in mind. And indeed, it's dominating strategy. And we can even, this notion of weakly dominating strategies is rather weak. So it's not the best one. But there is a second statement, which is a bit more complicated, but which tells you, oh, this is really the best solution for this second price auction. So, but I need just to introduce something for the next result. We will assume something. We will assume that. What does it mean? It means all players in this room will do the same strategy. there is no reason. Okay, no, there is a reason, but we assume that all players are going to have the same strategy. But of course, the price you have in mind is different. But the way you behave, you are all human with the same conditions, you are going to do the same strategy. This is an assumption. So I suppose that your strategy for player I is the same as for player J, any I and J. So it's called a symmetry assumption. Symmetry among players. Of course, it's a simplification, but I think it's already complicated enough. And the second one is that this function is increasing. This is a technical assumption on differentiable. What means increasing in this case? It means simply if you have in mind a big value for this, you are going to bid a big value. If you have in mind a very low value for this, you are going to propose a low price. So it's increasing. You have in mind a function, a certain theta I. If you move up this theta I, your action is also going to move, which is quite natural. If you, again, I put theta, it's a natural idea. If you have theta I in mind, the price you propose is like this. The bigger valuation, the bigger value you propose. So it's a natural assumption. Differentiability is technical. And as I said, there is a second proposition which is stronger than what is here. The pure strategy profile A hat, which is A1 hat up to AN hat. This is a pure strategy profile given by AI hat of theta I. Is theta I? So you have in mind theta I. You propose theta I. Is a unique. So now it's a stronger result. It's a unique symmetric. The unit symmetric differentiable. And increasing. And increasing profiles. Which is a Bayesian Nash equilibrium. For the second auction price, or the second price auction. So as I said, this is more than the previous statement because it says that, oh, this is a unique Nash equilibrium. So this is the best you can do. Propose a price you have in mind. You're not going to lose anything. Okay. And it's unique. And the proof is a bit more complicated, but still it's doable. Okay, now I said for the first price is more complicated, quite surprisingly. Because for the first price, you shouldn't propose the price you have in mind. So you can wonder, what should you propose? And I'm going to quickly present it, and then we do a very concrete example. If you have any question, again, you can interrupt me at any time. And I hope the notes are useful. So for first, I need to introduce one or two objects for first price auction. So remember, we had this distribution rho, which is a distribution for the price you have in mind for this object. Yeah, it can be anything. Okay, it's a probability distribution. So I will introduce set f theta, which is this integral 0 to theta rho of x dx. This is for given theta, it's called the cumulative function or the cumulative distribution function. Distribution function. So it's the integral between the minimum value, which is 0 to theta. So it's a definition, it's called the cumulative distribution function. And now, I'm sorry if you have never heard about random variable, I need to say a few words, but okay. If you haven't, just try to guess what is going on, and you will learn it more in the future. If x, capital X, is a random variable, it's just a word, it's a random variable, so it's a function associated with rho. With this, oh, by the way, I should put it in red. This one was a red one. So with, you know, it's something random. You don't know which value each player is going to decide. So it's called a random variable. And so it's this function is associated with what we call a random variable. Then what I just denote by f of theta is nothing but the probability that you choose a number between 0 and theta. The surface below the curve between 0 and theta is a probability that you choose a number theta here, which is quite natural. So this is a probability of the probability that the valuation of the object, the valuation is in 0 theta. This is a cumulative. Now, I want to do this for n-1 player. I need to introduce this. If I choose a different letter, if z is a random variable, for having n-1, be careful, it's n-1 and not n-1 bits. So it means n-1 player propose something smaller than theta. Remember, the players are independent, so you can guess the probability then. Oh no. Yes. The probability that z is smaller than theta, that n players propose a number smaller than theta, they're all independent. So it's just the product of what one players propose for the probability is that one player proposes a value smaller than theta power n minus 1, which means this is what I call f of theta power n minus 1. I've used here that all players are independent. Of course, if they are dependent, I couldn't say this, but we assume that they are independent. Okay, so this is something I have to introduce for the following statement. This notion of area below the curve, which represents the probability that you propose a number between 0 and theta, is quite natural. And if you have n minus 1 independent players, it's quite natural that you have this quantity power n minus 1.
Example, us filling a bin.
Coming to a concrete one, but you know, there are many things to do. So the proposition for, we consider a first price auction. Then the statement, it corresponds to the second one for the other auction. A1 up to AN with, now you will be surprised because this is not something I have introduced, theta I. Before this was just theta I. Now the claim is that this is a complicated object, which I will compute on a specific example. C theta I. So is a unique symmetric. I will explain this a bit. It's a unique symmetric differentiable and increasing profile, the same end of the sentence, profile, which is Bayesian Nash equilibrium. Okay, so the statement is essentially the same. There exists one profile, more complicated, but the same for all players, which gives you the best solution. The problem is this guy is complicated. It's called a conditional expectation. So don't worry, we will do an example where we can compute this explicitly, but this is why I didn't want to present the general theory. This is called a conditional expectation. I'm claiming that if you do in the discrete case, this is quite simple. Unfortunately, it's not, we could have drawn this game discrete, but we are in the continuous case, so I need now to tell you exactly how to compute this on a concrete example. So we have just enough time for this. So if you have never seen this object, look at what I'm going now, because it's a concrete exam application. But what it tells us again that there is only one Bayes Nash equilibrium given by a certain formula. So let me compute this on a simple example. And then you know what to play next time. So I'm going to consider, for simplicity, nu bar is 1, which means nobody is going to propose more than 1 yen for this. No, 1 is 1 million in this case. Okay, I just normalize. It doesn't matter. I put 1 as a maximal price. So 1 times 10, 1 man. Yeah, it's 1 man yen. So that's fine now. But it's 1. That's it. Now, what is the, how is my red? I need to define this rho. Remember, rho is a probability distribution now on 0, 1 to R. I'm going to take the simplest case. This is a function which takes the value 1 all the time. It means there is the same probability to give any price. This is called the uniform. Rho is a uniform distribution function. On 0, 1, which means that rho of any x is 1 for any x between 0, 1, which is probably not very realistic because it means you can propose any price between 0 and 1 with the same probability. I don't know if it is true, but okay. I mean, we can do the computation easily. So it's called the uniform distribution, the same for any. So now we can compute this f of theta. Remember, it was the integral from 0 to 1, the rho of x, sorry, not up to 1, up to theta. I'm sure you can compute this because it's the integral from 0 to theta 1 dx, then you get theta. That's it. Okay. What is P? The probability of z smaller than theta. I'll remind you, oh, it's not this. The probability that n players propose something smaller than theta, I remind you, n minus 1 player. I just take this theta power n minus 1. And now I need to compute this. And precisely, I didn't introduce the full theory because it's complicated. So let me do the computation, how we can compute this. So my aim is to compute this conditional expectation. It's done in 2 steps. This function has density. The density of this function is given by d over d, the derivative of this function, p of z smaller than theta. It's the definition of the density. You differentiate this, so you get n minus 1 times theta power n minus 2, right? Okay. And then this conditional expectation, and this AI of theta I, which is, by what I said, this conditional expectation of z was this, the expectation of z knowing that z is smaller than theta I is given by a certain formula. It's a probability that z is smaller than theta I times the integral of z f, yes, f of z dz. Okay, so this is the formula. So remember conditional expectation, you have something on the denominator, and the condition is that it's a probability that z is smaller than theta I. And this expectation, all expectations are given by a density times a variable. So this is a general formula for the conditional expectation in this case. So now you can compute, because the denominator is written there. It is theta. This was for an arbitrary theta. Now I'm for theta I. So it's theta I power n minus 1. Integral from 0 to theta I of, okay, I use the variable z, but it is this function. This is f. Oh, I didn't write, sorry. I didn't give a name. Usually we use, for the derivative, we use a small letter. So this function is what I called f. It's a density, sorry. So we have the integral of z, this function, which is n minus 1 times z power n minus 2 dz. I'm confident that you can all compute this integral. And I give you the result. You should get n minus 1 divided by n theta I. Hope you find this. You have to integrate z power n minus 1. It's 1 over n times z power n. You evaluate at theta I. You divide by theta I minus 1, and you get this. So what does it mean? Look, this is the Bayes-Nash equilibrium. What does it tell you? It tells you something surprising. For this second price game, if you have in mind that this has a certain price, you should not propose this price. You should propose n minus 1 divided by n of this price. This is the best thing you can do. Which is, of course, there is one assumption, which is this uniform. You know, I put a row uniform. This is probably not realistic, because it means you would put the same price for this object without any preference. This is not realistic, but think about it. I choose this simple case because I can really do this computation. If you put a more complicated function, so if you put something like this, probably you won't be able to compute this. And then you can do it numerically, but you cannot do it explicitly. So this assumption is probably not realistic, but at least we can do the computation. And with this assumption, we get that the Bayes-Nash equilibrium is obtained not by putting just theta I like in the second price auction, but by putting n minus 1 over n, which is a bit surprising. Okay, I will stop here. In the notes, there is still one result related to this. You can read it. With these two examples, I wanted to illustrate everything. We had a prior belief, then we bid then we put a price. This is our theta I. So we have information that nobody else has, and we can continue. I encourage you, if you look in the literature or internet, you will see many other examples, probably simpler. It's very good time to work on a concrete example. I remind you, the next lecture will be recorded, so you can watch it whenever you want. It will be available in a few days. And on 25, there is no lecture, but please use this time for working on some reports. Okay, thank you.